This video is part 1 of a 3-part series to help you choose a camera and lens for a Bath interferometer. First, we need to know what the camera lens is doing. If you put a piece of paper behind your interferometer, it will project a nice-looking interferogram. And so you may come up with the idea to use a lensless sensor instead of paper. For example, a DSLR camera with the lens removed. But this is a very bad idea. Here is a simplified diagram of an interferometer. I'm only showing the return test beam, not the outgoing beam, and not the reference beam. I'm showing a splitter cube just for scale. The return test beam typically bounces off a flat, but we don't even need to show that for my explanation. This point here is where the laser light returns to a point from the mirror. If you are exactly at focus and your mirror is a perfect sphere, then this point here is at your center of curvature, COC. If you have tilt or defocus, this point won't be quite exactly at COC. It will be moved in X, Y, or Z, but the test beam will still come to a focus somewhere. The splitter isn't relevant either for what we're talking about, but I leave it visible for scale, and because the COC is typically inside the splitter, it's a visual reminder that it's hard to get a camera lens right up to the focal point. This diagram is accurate for a 12-inch f3 spherical mirror. 12 inches is about 300 millimeters. Sorry for mixed units in this video. Now let's assume you have turned down edge on your mirror, meaning the edge of the mirror is a bit low. This blue line is the portion of the test beam coming from the bottom of the mirror, but because of the turned down edge, it's angled down a bit. I did this simulation assuming the bottom 10 millimeters of the mirror angles out by 2 waves at the edge. 2 waves of TDE may seem like a lot, but by exaggerating the tilt, it's easier to see the problem. You can see the blue line passes below the focal point, which is fine so far. Now let's say we have a DSLR camera with the lens removed. This green line represents the camera sensor. As you can see, the bottom of the mirror is imaged at the wrong spot on the camera sensor, somewhat more in the middle of the diagram instead of at the edge, where it should be. See, the blue line is low when it passes the COC, and it's still low when it reaches the sensor. This is a problem, as the edge of the interferogram doesn't represent the edge of the mirror. This will distort the interferogram in a bad way. Now let's add a lens. The camera lens, if focused on the mirror, will perfectly refract that beam of light to the correct spot on the camera detector. Amazing! Why? That's how lenses are supposed to work. For example, you photograph a person. This is the person. This represents the camera lens, and this is the detector. All the light from the top of their head goes outwards in every direction, and some of the light hits the camera lens, but the lens focuses all those light beams to one spot on the detector, even though they come to the lens at different angles. Here you can see the light coming from the person's hand is all focused to the correct corresponding spot on the detector. In a sense, the lens knows where the light is coming from and focuses it to the right spot on the detector, regardless of angle and lens position. This principle holds with our blue turn-down edge beam, which hits the lens at a different angle and location on the lens, but the lens focuses it to the correct spot on the detector. If you use no lens at all, or if the camera lens is out of focus, then the I-gram pattern that reaches the sensor won't correspond to the right part of the mirror you are testing. Without a focused lens, point A in the I-gram on the sensor might correspond to point B on the mirror being tested. You don't even need turn-down edge for this to be a problem. Any surface deviation will cause a slope deviation, which will necessitate a camera lens. Let's look at a perfect parabolic mirror. Now the light from the mirror focuses into a more complicated area. Optical engineers call this shape a caustic, this white area shaped like a Y in this example. If I switch back briefly to a spherical mirror, the COC is here. With the parabolic mirror, the light from the center of the mirror is focused at the same spot, but as you move outward in ring-shaped zones, the light is focused more to the left and the outermost ring is focused here. I set things up so I can highlight 10% of the mirror at a time. Here in blue is the 10% of light from the top of the mirror. We can zoom out and see it coming from the top 10% of the mirror. Here's area 2, 3, 4, 5, 6, 7, 8, 9, 10. Notice how each region of the mirror is exactly the same size. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's because, well, that's how I wrote the code. But because it's parabolic and not spherical, the light is coming in at all kinds of angles. The top tenth looks a little weird here. If the sensor was here, it would be less than a tenth of the sensor. As I go to the next tenth, it gets a little wider, 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 same, narrower, 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 narrower. So it's all distorted. But the lens fixes everything. So here's the top of the mirror hitting the bottom of the sensor. By the way, the image on the sensor is upside down, but that's true for any image you take with a camera. The image is flipped back around electronically. So here's the top of the mirror reaching the bottom of the sensor. Each of these are 1/10 of the whole image, just the way you want it with no distortion. Here is a typical image of a focused and unfocused eyegram. You usually get these sharply bending fringes at the edges, and also you often get a thin black or red line near the edge of the eyegram. So, takeaways. 1. You absolutely must use a lens. 2. It needs to be focused on the mirror being tested. If you see this pattern here, you probably forgot to focus the camera lens on the mirror. You can do it with the laser off if that helps. It's okay to focus through the prism. In fact, it's recommended if you have the camera aimed perpendicular to the mirror. Please watch the next video, part 2, Why Many Lenses Won't Work.